So what we want to do now is to go through some of the basic mathematics of a deep learning method called a neural network. So neural networks are normally characterized by what we call affine transformations. That means, in essence, that what we are dealing with is a series of matrix and matrix vector multiplication, where we transform the data from an input to a final output. So the unknown parameters which we want to train, and this is where the training comes in, are given by so-called biases and weights, which then determine the architecture of a network. And these are the parameters which we want to optimize in order to, for instance, find a solution to a differential equation, or we have some data which we want to reproduce, and we want to train a model which minimizes the discrepancy between the data we want to reproduce and what the model is giving us. So that's a kind of overarching idea. And there are two parts in a neural network. One is a feed-forward part, where you actually send in the input. You have initialized these unknown parameters to some specific values, and then you produce your first output. This output is compared via a mathematical function, which is called the cost or loss function, with the target values, the data we want to reproduce. Then we optimize this function, the output of the network. So that's the feed-forward pass, which ends with producing an output. This output is then compared with the target values we want to reproduce. And this is where the optimization starts. So we calculate the derivative of this function we have decided upon, which is called the cost function or loss function. And then we propagate these derivatives backwards using the chain rule. This is called the back propagation algorithm, which is an implementation of the chain rule. And it allows us to calculate the gradients of the different parameters. And we want to drive these gradients to zero, essentially. And the training is then done in two stages: a feed-forward pass, where we produce a given output, and then we go back again and update the unknown parameters. We have a new set of parameters, and then there's a new feed-forward stage. And then we go back and forth till this function, which we use as a gauge for measuring the quality of the model, reaches a specific value. This is essentially what a neural network is about. So it's a training by calculating gradients, and these gradients are calculating with an algorithm which is called automatic differentiation in its reverse mode, or as it's also called, the backpropagation algorithm. So the backpropagation algorithm is nothing but you implementing the chain rule on the derivatives, as you will see on the whiteboard notes to come pretty soon. And then this application of the chain rule gives you the expression for the derivatives. That is a neural network in a kind of, from an overarching point of view. And normally it consists of a set of hidden layers. And we are coming back to the famous theorem, which is called the universal approximation theorem. So we will just cover that one just in a few moments. And we are going to have a set of parameters for every layer. And this is normally indicated by a collective container, theta. So boldface symbols are either matrices or vectors or higher order tensors. And these parameters here, they are related to the parameters in other layers for a series of affine transformations, as I said. So there is a feed-forward stage, which takes a given input and produces a final output. And that's compared with the target values through this cost or loss function. I tend to call it cost function. Some people prefer to call it the loss function. Other people call it the error function. But this is where you gauge the quality of your model. And then there's a backpropagation stage, as we discussed. And these two steps, they define one iteration. So one update of your parameters. And a typical calculation can include thousands of such iterations. And if these matrices are big, you see immediately that you may run into a huge consumption of CPU cycles, because you're essentially dealing with matrix, and matrix vector multiplications. And the more parameters you have, the larger the matrices and the vectors you want to define in order to set up the parameters. So the network, so we would typically have some function f, which aims at describing some final result or outputs. There are some typos here because this was done on the fly yesterday. So I'm going to correct all the typos, as you can see. And given a specific input, and the architecture consists of an input and an output layer, where the input layer is defined by the inputs. And then the output layer produces the model output, y tilde, which is then compared with a target value y. So when I write y without the tilde on it, this is, for example, an experimental observation which has been labeled. Then you have a given number of hidden layers and neurons nodes. So this is actually your model or architecture. You have a given activation function which takes in an input from a previous layer and then produces an output for that specific layer. And these activation functions are functions which people play around with as a parameter. So what you see now is the model or the architecture. So if you're fitting a polynomial, you know that you could fit a polynomial to a given degree. That is your model. If you're using Fourier theory, you have a Fourier expansion in terms of some terms. That is your model. The model here consists of the input and output layers, the hidden layers, the number of nodes, finally, the type of activation functions which are dealing with, and also a given cost function. So the cost function is something which you tailor to the type of data you're dealing with. So this is data specific, the type of cost function which you end up with setting up. And if you deal with linear regression, as we discussed quickly last week, then you would have a model which is linear in the unknown parameters. Pay attention that this is not the general case. If you deal with a neural network, there is not a linear dependence. What you should replace this with then is a function f, which depends on the input and the parameters theta. So just keep that in mind. The expression which you see here is tailored to a linear regression problem. So you have a linear dependence in terms of the parameters theta, and this x, which is called the design matrix, is the one which contains your input variables. So you can simply have a value for x in one dimension, or x can be a three-dimensional object, or it can have many other features. And that depends on your type of simulation and data which you have. So for neural networks, these parameters are given by what we call weights and biases, which we are going to define rather soon. So I'm going to switch to the whiteboard pretty soon. I just wanted to go through some of these basic things before we dive into the whiteboard. So the weights are given by these matrix elements, and where the superscript indicates the type of the layer which we have. And then the bias is typically given by a vector element, which is given here by J for the specific node J in that layer number L. So when you have defined the architecture, which is your model, then the optimization of the cost function with respect to the parameters. So we take the derivatives of this function, the cost function, or the loss function, and then we calculate the derivatives. And these derivatives are then used to find we want actually to find the roots of the derivatives of the cost function. And there are tons of ways of dealing with that. So if you have a few data, you can use Newton-Raphson or quasi-Newton methods, which are often very efficient and very precise. So remember also that the methods which we are dealing with are approximations to a Taylor expansion of the cost function around the optimal value. And this Taylor expansion is truncated at the level of the second derivative. This is mathematically what leads to Newton's method. But Newton's method, since we have many parameters, that means that we have to invert a matrix which involves the second derivative of the cost function. And we don't want to do that. That's normally called what's the name of that matrix? Does anyone remembers that? It's the Hessian matrix. So what you often end up with then are gradient methods where you may have a constant parameter, the learning rate, or you can find ways to approximate this learning rate with information about the gradients. And that leads to popular methods like adaptive gradient, root mean square propagation, and perhaps the most popular method of them all, which is called ADA. We're going to discuss some of these methods because this is actually important. And this is a very, very active field of research. And I always said some jokingly that if you want new friends, this is actually one of the fields where you will get friends which will cite you. Because this paper, ADA, which came in 2014, has more than 150,000 citations. That says everything. A good scientific paper, a good one, has 100 plus citations. If you're getting close to 1,000, that's an excellent paper. When you have 150,000, you're just in another league. But that tells you about how important this is for the convergence of this iterative process. Because you are dealing with billions or millions of parameters you want to optimize. So the surface you want to optimize is really a multidimensional surface. You don't know whether this is a convex function you want to optimize or a concave function, whether you will be stuck in a saddle point or a local minima or global minima, etc., etc. So that means that when we deal with neural networks, we are going to calculate these derivatives again and again and again and again. And that's really the time-consuming part of any machine learning algorithm. So anything which can speed up this kind of Newton-like methods is very welcome. And there's a lot of research in this field. So we will mention some of it a little bit later. And many of you have encountered these things like stochastic gradient descent and the whole family of different methods there. So there are also additional parameters, so-called hyperparameters, which we can add to the cost function, and that gives a different optimization problem. We will also come back to that a little bit later. So at the end, and some people get really disappointed because you have a feeling that you're just dealing with parameter tuning. And if you think of it, if you look at a project like Google's DeepMind, where most of the money actually goes into is the training of a network. So the wage budget of Google's DeepMind was in 21, $1.2 billion US. You can compare that number with the Norwegian so-called billion on AI, which is scattered over 5 years, so 200 millions per year. I mean, the government made a promise of investing in machine learning and artificial intelligence. So Google's, just the wage budget for Google's DeepMind was $1.2 billion US per year. And in addition to that comes the CPU cycles you have to pay for in order to train the networks. And this is where a huge part of all efforts go into, in the training of the parameters. So when you have a data set like ImageNet, which contains millions of images, which you use to train different models, the training of the network is actually extremely time consuming. So in our case, as I mentioned last time, we will often stay with the simpler models, simply because we don't have access to these resources. So I wanted to, before we take a break, to say something about a very important theorem. And this is the theorem which actually sparked a lot of interest in neural networks back in the 90s. Then the field died out a little bit, simply because people were using the sigmoid function, and the sigmoid function as an activation function could often lead to gradients which vanished. And you can see now that because the sigmoid function, when we come back to that after the break, actually goes to 0 in these limits. So it goes to a constant, which means that the gradient goes to 0. And there was a famous paper by Glorot and Benjo, so one of the textbook authors of one of the textbooks we recommend, where they actually demonstrated that some of the problems with the training was related to the way you initialize the weights and also the way you set off the activation function in terms of the sigmoid function. So that really sparked much new activity in deep learning. So there was a huge wave, a surge back in the 1990s with Sebenko's theorem, which simply states that if you have any continuous sigmoidal function, then given a continuous and deterministic function f of x, and this is done on the unit cube, you will see the same if you're taking a course in real analysis. If you look at, has anyone heard of Weierstrass theorem? Yeah, so that's used to prove that a polynomial gives an approximation to a given order. You can repeat the same with Fourier's theorem. So Fourier's theorem is also gives you a similar approximation error theorem for the approximation you make with a given Fourier series. So given such a function and a parameter epsilon, which is larger than 0, what Sebenko actually showed is that there's a one-layer hidden neural network. And I will use this symbol F and replace that with, this is my Y tilde. So this is the model, which, or what the network gives. And this network now contains the parameters theta, which have the weights, which is typically a matrix, and the biases given by a vector. And it simply says that this is less than this parameter for all values of x. And for those of you familiar with the Stone-Weierstrass theorem for polynomial approximations or convergent criterion for Fourier series, there are similar proofs which are being used. So I'm coming back to this a little bit later. So this was actually modified by Honig. So what we're saying is that any continuous function supported on the unit cube in d dimensions, if you scale the results to be on the unit cube, that can be approximated by one-layer sigmoidal network to arbitrary accuracy. So Honig extended actually this theorem by letting any non-constant bounded activation function to be included. And what he used is the expectation value, the assumption that this function is bounded. So this is a probability which we haven't defined. So this is a definition of an expectation value. And X is element of this d-dimensional space. And then what you can show is that the difference between these two squared is smaller than a number epsilon. So this is what Honig did back in 91. And this really laid the foundation for really a surge in interest in deep learning methods. However, it was after 2010, which is a kind of year we used to mark as the kind of deep revolution start, because we have many other machine learning methods like decision trees, random forests, support vector machines, which for the latter one are just plain linear algebra applications with optimizations. But then the deep learning revolution, we can really say that it started in 2010. And since then, this has just, exploded. So these are fundamental theorems. We are not going to prove them, we will just cite them. And the thing is, what you should keep in mind is that none of the proofs give any insight into the relation between the number of hidden layers and nodes and the approximation errors, nor the magnitudes of these parameters, W and B. And they have a kind of universality. We may say that it gives a kind of universality, no matter what function we want to compute. It does not mean that an NNN can be used to exactly compute any function. What you get is an approximation that is as good as we want. So just keep this in mind. And there's a class of functions in the theorems that can be approximated, continuous ones, but we also tend to apply them to non-continuous functions. Sometimes we have no idea, we just apply it. And sometimes you will see statements in the literature that we use this and this neural network parameters, we got an excellent reproduction, but we don't know why. Okay, so there's a lot of this kind of trial and error in the field. However, the theorems are pretty clear, but you may actually find that a neural network may still give an approximation even if we fail in some points. So these are kind of hands-on experiences which many people actually gain in using neural networks. So what I was thinking of is that we take a small break, and then I actually wanted to go through on the whiteboard some of the basic mathematics before we then, next week, we have a discussion of different project paths and start also looking at in more depth and setting up codes, etc., etc. So I'm going to put the recording on pause. So what we're going to do now, and I hope those of you who have written a neural network code like last semester don't feel this too boring, but we are going to go through some of the basic mathematics of a neural network. And we will continue with that next week as well. And then we will also discuss the basics of the codes. You will find a code example in the slides for this week, but we will probably not get time to go through it today. So that means that we will spend more time on the coding part next week. And at the same time, we will also have this mini workshop where you guys present possible projects. So if you're dealing with a type of regression problem, it's pretty common to define this cost function to be given by what's called the mean squared error. That is something which is widely used. And this is something which emphasizes the squared error. So if you have large deviations, they will be emphasized because you square them. And the y without the tildes, these are the target values. This could be the result of a measurement which you want to reproduce. And then the y tildes are the results of the network. This is what the network produces. So I wanted to bring up an image here so that you can roughly see the kind of layout which we are going to deal with and the different parameters. So we are going to define an input layer which contains a specific set of inputs. So for me, who runs often calculations for quantum mechanical problems, these inputs would be the positions of a given set of particles. So if I have 10 particles in 3 dimensions, I would have 30 input values. These would be the positions of the particles. And then I can have many of these positions, which means that my x becomes then something which reflects many, many possible positions which different particles can have. And then it would typically be translated as a matrix and not as a plain vector. That's one possibility. And then these parameters which you see here, these a's, these are the a's. When you see this parameter here, that's the output of a given node in one hidden layer. So you're feeding in some input from x1, x2, x3, etc. to this A1 or this node 1 in the first hidden layer. So the superscript 1 here refers to the hidden layer, and the subscript refers to the specific node which you have. So this is the output. This output is then fed into the next layer. And this produces a new output to the next layer, etc., etc., etc. And you can have a network which is very deep, or you can just have a shallow one. So typically when you train the parameters, you would then start with just one hidden layer. And then you increase the number of nodes or neurons, as they're also called. And then you train your results, you produce an output. So this is what the network produces. So you would initialize everything here with a specific value or some random values for the unknown parameters, the weights and the biases. And then you feed this information through the network and you produce an output. So if I'm, suppose I want a function value with a given set of input values, that could just be one value. So here I have 3 or k output nodes. If I have a binary classification problem, I would typically have only one output node, either 1 or 0. It just produces these 2 values. If I have classes like discrete classes of handwritten numbers, which is a famous data set many of you have encountered. If you go into that textbook by Raschka, you will see that as an example. Actually, the Jupyter notebook, which Raschka has presented for chapter 11, has the MNIST data set. And these would be 10 handwritten numbers from 0 to 9. And that means you would have k, which you see on the output, would be 10. So then you would have 10 output numbers. So all these connections here, so all the nodes are connected, and that gives you dense matrices which connect one layer with another one. And when we perform the matrix multiplications, we call these mathematically affine transformations, which means that we are calculating 2 dense matrices and multiply them with each other. So we don't make any truncations. This clearly, when we are dealing with images, as we will see when we come to convolutional neural networks and the mathematics of those, then this is going to lead, if we insist on this, is going to lead to matrices of huge dimensionalities. And we would like to reduce the dimensionality. So in a way, everything we deal with from a practical point of view is dimensionality reduction to some effective degrees of freedom. Actually, I would claim that all of science is to find an effective representation of some specific degrees of freedom. That's my view of science. I am, from a philosophical point of view, I am a reductionist and materialist, I should also say that. From a philosophical point of view, that was a digression. Then you're peeping into my soul here. Okay, so the thing which I want to do now is actually to switch a little bit over to some of the definitions, and we are going to move over to the whiteboard. But if you now look at these inputs which we have to a given node, so if you look at this variable here, that receives an input, that specific node, and that is modulated by an activation function. So which means that you produce an input in here, and that input is given by these weights, which connects the output from the previous layer. So if you look at this one, you see this receives input from this one, that one, all these nodes. And that is reflected in this variable, L-1, the previous layer, multiplied with the weights which connect them, and plus a bias value. And this bias value is normally introduced in order to avoid that the input is 0 by accident. So you would typically offset this B value to some kind of small random number, just to hinder that if in case the weights are by accident equal to 0, because if they are, the training would stop. So that means that we are producing an input to the given node. There's a node J in this layer, and you can now rewrite this in terms of a matrix times this vector. Actually, this A doesn't need to be a vector. It could actually be a matrix. So just keep that in mind. Huh? So that means that you end up with matrix or matrix vector multiplications. And B could also be a matrix. This depends very much on the way you represent your data. Okay? And then this is normally fed through an activation function. And this activation function is normally written like a sigma or f if you want to be more generic. But normally if you write a sigma here, this normally refers to the sigmoid function. So I will try to be a little bit consistent, and I'm actually going to use not an f, but a sigma later on, just to indicate that this can be any activation function, just to distinguish that from the model which we will produce. But this is a famous sigmoid function, and this was the one which were used in Sebenko's proof of the universal approximation theorem. And then Hornick and company, they actually modified that one to any bounded and continuous function, actually also discontinuous functions. We will come back to types of activation function. But this variable a, which you see here now, in here, this is the output of that activation function. What is pretty common when you now deal with different types of problems, if you're dealing with a classification problem, what is common then is that this outer layer has this output layer, not outer layer, but output layer, has an activation function like a sigmoid. So which means that if it's below a specific value like 0.5, it spits out 0. If it's larger than 0.5, it spits out 1. If you're dealing with a regression type of problem, it's common not to have any activation functions at the output layer. You're just spitting out the value which comes in. And that would be the function value, which you then would compare with some target values. So these are some of the basic mathematical operations which we're going to do. So what I'm going to do now is actually to switch back to the whiteboard a little bit, just to slow down the pace. So let's do that. So if we now look at what we have defined. So suppose now we look at one hidden layer only. Let's take that one first. And then we have now defined m input nodes. So that means that the weight matrix is now going to be a matrix of dimensionality m times n. And then we're going to have a bias vector, which will be a vector if we now assume it's a vector. This may change, and this is a vector of length n. And then it means that our matrix is going to be, if we now write this out in terms of vectors, there's going to be a vector W0. That's the first column. I have a W1, etc., up to a Wn minus 1. This is just if we write this in terms of the column vectors. Then the input x is then modulated to give an input to the different nodes, various nodes. And this is now modulated so that we have a z. And I'm now writing this as vectors or matrices. So I am not going to put vectors or things like that or bold-faced it. And I'm just simply going to say that from the context, you will see that this is either matrix or vector. And this is now given by the transpose of this one multiplied with x plus this bias. So this is z, which is now the input to the nodes in the first hidden layer. And in this case, we have only one hidden layer. So we have also assumed that x is now a vector of length n. So what we're doing next is that we're going to produce an output. So this X is now going to here, move into, so X moves into this sigma, which now has some function Z value of X plus B. And now for the sake of simplicity, I'm just going to call this for sigma, since I'm writing this as a matrix of A of X. So that means that this is going to produce an output, node 0 of X, node 1 of X. So these are the different nodes which we have, n minus 1 of X. These are the specific outputs for that hidden layer. So what we are doing now is that if we now look at this graphically, so let's redo that. So we now have an input layer. This produces an input to the specific nodes. And I'm just writing this like this. And this is the first hidden layer. And this produces an output. And this output is something which I will call for L. And we also label this as a Y tilde. Okay. This one is now fed into a function C of all the unknown parameters theta. And this is compared with the target values. So these are our target values. Then this is the overarching structure of it graphically. And then you would open it up and write the specific nodes for the input layer and the output layer. So this would be L equal to 1. This is actually L equal to 2, but we write this L which you see here, this one, this is for the output. Okay. So if we open it up, this is going to look like as follows. So when we open it up, we will have now, so let me also have this one, hidden layer. So these are the variables which I will use throughout the semester. So when we open it up, what we have then is an input layer, as you saw from that figure in the slides. So we will have x0, x1, down to some x m minus 1. And then we have the hidden layer. And that can have a given number of nodes here. So we will then, let's say that this produces an input. So we are going to write this as a sigma of A of Z0 or 1. And that produces an output of A0 or 1. So I will just write, let me just write these bubbles, these circles a little bit larger. So here I could now have A1 of layer 1. And here I could have A n minus 1 of layer 1. And these are all connected. Etc., etc. And then we can have a given number of output nodes. So if I'm looking after specific function value, so if I have a three-dimensional function, then I could have X, Y, and Z as input variables, 3 input nodes. And then I could have just one output, which is the function value. And then clearly I can plug in many more input values, because one of the things you will have to, or you will realize pretty soon, is that everything we deal with deep learning are data greedy methods. The more data you provide in the training, the happier the networks are. So that means that typically we would feed in lots of input data. So if I have one position, X, Y, and Z, I would feed in hundreds of positions. So that means I would typically translate what could be a vector X into a matrix X. And similarly, I would also produce a series of outputs. That means that often then, instead of matrix vector multiplication, as we showed in the simpler case, we end up with matrix multiplications. And in this case here, we have an output layer. And these feed into a specific number of nodes. So we can have, let's say we have 3 nodes here. So this would be my A1 in this, oh, so A2, sorry. No, A0 of layer 2. This would be A1 of layer 2. And this will be A down here of some K minus 1 of layer 2. And in our case, the output layer is labeled with the uppercase letter L. Now, these outputs then fed into this cost function. And this cost function is going to depend on the outputs which we have. So which we will label more generically as a y tilde. So these labels here are changed when we move into the cost function with a y tilde. There will be a target value, and then we will have the parameters theta. And this is a function we want to optimize as a function of the parameters theta. So what we typically have, if we have a mean squared error, we want to drive the mean squared error to 0. In order to do that, we would calculate the gradients of the mean squared error and drive them to 0. And this is what we want to do in the training. So if you now look at a repetition of this multiple times, so if we go back a little bit, you saw now that I call this generic function here for an A, uppercase letter X. So let's just look at the neural network in a more generic sense. So if we have many layers, I'm going to produce an output, uppercase L, and then I'm going to have L, which starts from 1, the first hidden layer, till the final output layer. So normally we call also the output layer as part of this set of layers, but you would say now that the number of hidden layers are actually from 1 to L minus 1. And it's pretty common that the final output layer has a different number of nodes from the hidden layers. So when I write this number L here, or this character L, for the output layer, this is actually a visible layer. So you could say now that you have the input layer, which is visible to you, and the output layer, which is visible to you. And then you have some black magic, which takes place inside the network, which is then represented by all the hidden layers. So what you see is the input and the output. Okay, so what you would have then is then a series of such layers. So what you would do then, if you have now a loop, and this is a set of transformations which we end up doing of L less than L, what we would produce then is that this y tilde is going to be a function of X and these unknown parameters theta. And this will be a series of affine transformations, which are now given by this activation function in the last layer. This is a function of A of L, and this is a function of sigma of L minus 1. And then this continues all the way to the first hidden layer, where we have A1 as a function of X. So you can think of now this as a set of such matrix multiplication which go throughout the network. And every hidden layer has an activation function, and it's pretty common to actually use the same activation function throughout the network, except for the output layer. So you would normally have same activation function for all hidden layers. This is pretty common because if you're going to change activation functions while you train the network, you will have way too many parameters to train. Activations for all hidden layers. And then what we have is a different activation function for the output layer, because that depends on the type of data you're dealing with. If you have a classification problem with 10 images, then you would typically have 10 output nodes. Different activation functions for output layer. So the training of all these parameters goes then through these back and forth, where you feed forward, you produce an output, you compare this output which you have, that means this quantity here, you compare that with the target values, and then you have a function, the cost function, which you want to optimize with respect to these parameters, and then you back propagate these parameters. So what we are going to deal with now is actually this so-called back propagation algorithm. So let's go a little bit more into the details here, because there are some minor technicalities which are always actually good to take a look at. So let's go into technicalities and the basic equations which we have to program. So what we have is a variable zj of L. So this is a given hidden layer L. So its structure is something like this. There's a sum from I. And now I'm going also to assume another thing. This is pretty common in the training of networks, is that you use the same number of hidden nodes in all the hidden layers. You can change them, but it's pretty common to just run through with the same number of nodes. But this is up to you. You can actually change the number of nodes. But we are going to say that these layers have m-1 hidden nodes, which it receives from the previous one. And then there is a weight which links the previous output with the new nodes. So there will be a variable of ij, and then I have my index L. So these are the weights for that specific layer, the unknown parameters. And this is then multiplied with the output from the previous layer, which is on L-1. And then we have a bias variable of bj of L. Is my handwriting okay? Okay, good. Then we know that this AI, the way we have defined things of L-1, is then given by this activation function in that specific layer, L-1, of Z of I of L-1. And since we have decided that we will use the same activation function for all the hidden layers, it's then just common to just write it like this. So this function sigma doesn't need to be the standard sigmoid. It can be any of all these plenty of animals which are defining various type of activation functions. So one thing you could do while you're listening to me now, if you want to, is just to search online types of activation functions, and you will get tens and tens of activation functions which are used in the literature. And often you will see people favoring some of them. We will come back to those which are the most commonly used. But the activation function becomes a parameter in your model or your architecture. So when I say model, I also mean architecture of the network. Okay, so what we are going to need now are some quantities, because what we want, so we want the gradients of this cost function at the output layer. So we want to drive that one typically to 0. If you're doing the mean squared error, the ideal is to have a mean squared error, which is 0. That's the ideal. So that means that what we would have then would be a gradient of this function, this cost function, which now contains y, the y tilde, which is the output. So this is what we call A of L, the output from the last output layer. And this is a function of theta. So this is what we want to do. Now, in our case, we have parameters in every hidden layer. So that means that when we are calculating this derivative, we need to take into account all the previous variables. So which obviously means that we have to use the chain rule. So let's look at a simple example here, because this is what we want. This is a training. But clearly these parameters theta, they are not limited to the output layer. They are contained in all the hidden layers as well. So let's look at a simple example here. And that really sets the scene a little bit for the kind of problems which we have to face and what we have to program. So suppose now that we have a simple example. So we have X, W, and B are all scalars, no vectors. This makes life often much easier. So this is just a simple example I cooked up here. And then we assume now that we have one hidden layer, and that means that L is equal to 2. So that's the final layer, the output layer. So we are then going to produce a function, f of x, the input, and as a function of these parameters theta, which is going to look like a sigma 2, which is the activation function for the final output layer. This is going to be given by the weights of that layer. And I said that we have only one parameter. So this is in principle just something which looks like this. So we have an X, and then we have an output which is produced here, an A1, and then we have an A2 here, and that's it. So that means that A1 and A2 are defined by W2. This is multiplied by A1, like that, but this is again sigma 2 of that one multiplied with sigma 1, multiplied with W1. So this has a parameter W1, and there is a parameter B1. This has a parameter W2 and a B2. And then this is now multiplied with X, which is fed in, plus this parameter B1 plus B2. So this is the same as sigma 2 of actually W2 of A1. Actually, I forgot one thing here. There should be, sorry for that. I actually forgot that one. So this is plus a B2 value. So this is given by this plus B2 here. Now, what we want now, we want derivatives. So we want a d of this specific function, or we actually want the cost function, this cost function C, we want a derivative with respect to W2. But we will also need a derivative with respect to W1. We will need a derivative with respect to B2 and dc of dB1. So we are going to need all these derivatives in order to optimize and find the new values. So I'm coming back to these calculations a little bit next week, but now I'm just going to set up the kind of scene and the kind of equations which we need in order to find these derivatives. Now for this specific example, when we are now calculating the derivatives, you will see that this is actually not that difficult to set up since these are scalars. So when you look at this dc with respect to W1, this is a quantity which would now come in when you calculate the cost function So the cost function, if you look at that one as a function of y and y tilde and these parameters theta, this is not an explicit function of the parameters w1, w2, b1, and b2. Because if you now have, as an example, the regression case with a mean squared error, this is going to be given by, and this factor of half is common because when you calculate the derivative, you get a factor of 2 multiplied with a half, so then you get rid of the factor of 2. So this now runs over all the data which we have, and we have n minus 1 data. So we have y minus y tilde squared. So this does not have an explicit dependence on theta, which in our case is a collective container of W1, B1, W2, and B2. And these are all scalars. So when I'm calculating the derivatives now, with respect to these parameters, I will actually have to use the chain rule in order to be able to do that. So that means that when I now set up the derivatives, I get an example of one of them, example of derivatives. So that means that I need the derivative of the cost function with respect to this variable y tilde. So there will be a dy tilde and dy tilde with dw2. That will be one derivative I will need. Now I know that this w2 depends on, and the parameters, they will depend on previous values. So what I will need to do then, when I go back here, is to include, through the chain rule, I will need derivatives of this type, etc., etc. So a typical derivative, which you will need then, would be something like a d of y tilde with respect to w1. That could be a derivative you will need when we are setting up the backpropagation algorithm. So what I'm doing now is to prepare you in order to see the complexity of the backpropagation algorithm, which then involves all these partial derivatives, because we are tracing ourselves back, because there is not an explicit dependence on the parameters here. So that means that we simply need to use a chain rule. Okay, does that sound reasonable? So a typical derivative, which you may end up having, would be a dy tilde of dw1. So if you look at that one, if we go back to the expression which we have here, which is this expression here, you see now how you can use the chain rule in order to get that one. So that means that what you would get then would be something which in this case looks like sigma 2, the derivative of that function. And then I have a w2 multiplied with sigma 1, w1 of x plus a b1 multiplied plus a b2. And this is then multiplied, since I'm now using these chain rules, the w2, and I leave that as a small thing for you to check. I get w1 plus times x. Well, let me just write this correctly. w1 times x plus a b1, and this is multiplied with x. So this would be the typical derivatives which we would get for one of these quantities. Now, there's one thing which I wanted to anticipate before we go on to the final equations for the backpropagation algorithm, because we need to set up all these derivatives. So one thing you will see now, if we generalize this to a given set of layers with L layers, then this derivative of this y tilde with respect to w1 is going to be a product of given functions. So we have L layers now. We start with the first hidden layer, 1, and then end with L. And then this is actually start with that one. So we have a WL here. And this is multiplied when we look at the equations, it's going to be multiplied with an L equal 1. So I leave this as a small exercise for you all. And then we have the derivatives of L, which is L prime. And then I have the input C of L. And this is multiplied. So this is a multiplication sign, but then it's multiplied. So let me put like this with the value X, the input value. So this is a multiplication sign, multiply. And the same here, just to distinguish it between these different variables. Now, what you see here is that if this sigma is the sigmoid function, and the sigmoid function takes the following mathematical expression. So C of C, sigma of C is 1 divided by 1 plus e to the minus z. This takes the values that it's equal to 1 when z goes to plus infinity and 0 when c goes to minus infinity. So what it means is the following. If you make a plot of it, it's going to look like this. So this is the sigmoid function. So we have 0 here, we have 1. So it's roughly going to look like something like this. Now, my hand drawing is not the best one. But this should be a constant here. So what you see now is that if you have values of z at the end points or large values, then what you see is that the function becomes flat. When the function becomes flat, it means that the derivative of this function is going to go to 0. If you then go back here, if that is the case, then you will get gradients which will be close to 0. Then what happens when you train a neural network in this specific layer is by accidentally, the gradient can turn to 0 and become 0. When the gradient is getting close to 0, the training of the network stops. So remember that the training consists of a given number of iterations, where each iteration consists of a feed-forward stage and a back propagation stage. So in the back propagation stage, the gradients are updated for each layer once. If you do it 1,000 times, the back propagation and the feed-forward pass, then your gradients get updated 1,000 times. So if by accident, one of these derivatives gets very small, then these gradients here may get close to 0, and the training may stop. So this was known as the vanishing gradient problem in neural networks. And it persisted roughly till this paper by Glorot and Benjo in 2010, where they showed that much of the problems with the training of neural networks was simply due to the fact that people used the sigmoid function as an activation function. Now, the sigmoid function has a very, natural understanding when you look at the graph here, because you could think now that if the value is larger than a half, then you give it a value 1, then it fires a signal. So it's very much inspired from neuroscience. If it's below a certain threshold, which you could think of as a certain voltage, then it just gives you 0, and it doesn't send out a signal. So when people proposed the sigmoid function, this was very much based on experience from neuroscience. So people actually used the sigmoid functions more or less by default. And many of the neural networks had problems in training. And after this paper by Glorot and Benjo, which I think now has tens of thousands of citations, the field, in a certain sense, just exploded. And the culmination is what we see now. And I guess it's just going to increase more and more with, let's say, ChatGPT and generative models and large language models. You will say now that since 2010, it's just 14 years. It's a very small time scale in terms of scientific developments. So we're just 14 years, and it has unleashed lots of creativity. Okay, so maybe I was a little bit slow now, but next week, and you will also find that in the slides, there is an explicit derivation of the equations, which we need to set up the backpropagation algorithm. So next week, we will have a presentation of projects for those of you who have some ideas. And then we are going to wrap up the discussion of neural networks. And we should start then thinking on how we want to use the neural network codes in order to get started with the project. So feel free to send emails, ask questions. Don't hesitate to do so. And also, if you have questions after the lecture, feel free to ask questions.